In this and the following lesson, we will try to figure out our place in space and time. First, we'll tackle space, and we'll use this drawing. Here we see some elements of our solar system. We have our sun, some of the inner planets, and asteroid belt here, and Jupiter. Now, you're probably familiar, there are 8 planets that orbit our sun, and we can define a solar system then as a star with orbiting planets. Something interesting happened on one of those inner planets, our home, the Earth. Around 4 billion years, life emerged. Now, NASA has a definition for a planet. It must orbit a star, be nearly spherical due to its size and the effects of gravity, and it has cleared its orbit of other material. So, for example, the Earth's moon is not a planet because the moon orbits the Earth, not a star. And the asteroids are not planets because they're not spherical. They're not big enough such that gravity would tend to smush it into a sphere. We can also take note of 2 kinds of planets that our solar system shows. The inner planets are what we call rocky planets. They're made of heavier elements like oxygen and silicon and nickel, aluminum, iron. And that's in contrast to the outer planets that are mostly made of the lighter elements like hydrogen and helium. For example, Jupiter and Saturn are mostly hydrogen and helium, just like our sun. Now, in the mind of a child, a star might be something like this. But in reality, stars are very different. Here's a beautiful picture of our sun. It is a giant ball of hydrogen gas, and something fascinating is going on in the core of the star. Stars begin as a cloud of hydrogen, and over time, gravity, which is an attractive force between all objects with mass, gravity can compress that cloud. As the compression continues, it gets hotter, and higher pressures and hotter temperatures inside the core of the cloud. At a certain point, it's so hot that nuclear fusion begins. So we can define a star then as a compressed cloud of mostly hydrogen gas, hot enough for nuclear fusion in its core. Now, the details of fusion are as follows. In the core of the star, the pressure and temperature are hot enough to fuse hydrogen nuclei into helium nuclei. And the energy released heats the surface of the star to a point where it glows. And that means emitting light and heat. So stars shine light because their surface is really hot. And their surface is really hot because nuclear fusion is happening in the core of the star. Now, stars then emit energy out into space, and that has an important influence on the planets that are orbiting that star. And scientists are very interested in a zone called the habitable zone. And we can define this as an orbital distance from a star in which water can exist as a liquid on the surface of the planet. And here we see for our solar system, the habitable zone is about from Venus out to Mars. In that zone, water can exist as a liquid on the surface of the planet, notably Earth. If you're closer than Venus, like Mercury, it's so hot that water would be in the vapor form. So it would be water vapor. You couldn't have liquid water. It would be too hot. It would just boil up. And if you're farther from Mars, the water is going to be in the form of ice. So the habitable zone is that zone where water can exist as a liquid on the surface of the planet. And scientists are really interested in this concept of a habitable zone because if we're interested in finding life elsewhere in our galaxy, we're going to want to look for the planets that are in habitable zones around other stars. And this is exactly what scientists are doing. They're trying to find lots of planets that are in the habitable zone and look for signs of life on those planets. Now, why do we need liquid water? Because on Earth, of course, all living cells have water inside them. And water provides the environment for lots of chemistry to occur. So we think life requires water because that's the way life is on planet Earth. And so we're interested in finding other planets with liquid water on the surface. Now, our sun is just one of several hundred billion stars in the Milky Way galaxy. All these little spots would be stars. And the stars are orbiting the core of the galaxy. Scientists estimate the Milky Way to be about 12 to 13 billion years old. And if the universe is 13.8 billion years old, then approximately 800 million years after the Big Bang, we have stars and stars organizing into galaxies like our Milky Way. Now, I've indicated the stars to be different colors here, and that's intended to capture the different sizes and temperatures of stars. So large stars that are very hot, the surface is very hot, tend to emit more bluish light. Cooler stars, smaller, cooler stars, tend to emit more reddish light, and then stars with a size and temperature in between those extremes are the sort of yellowish stars like our sun. This picture was taken by the Hubble Space Telescope, galaxy UGC 12158. It's about 400 million light years away, and it's in an orientation where we can see the structure of the spiral galaxy itself. We see the core here, and then we have the spiral arms around it. And scientists think this galaxy is like a mirror image of our own. Scientists think basically the Milky Way looks like this galaxy. Let's define our galaxy: a huge collection of gas, dust, and billions of stars and their solar systems, all held together by gravity. Now, this picture shows some stars in the night sky. Well, if we go out to a dark place away from city lights, with the naked eye we can see a few thousand stars. The stars we see in the night sky would just be the nearest neighbors of the sun. If we look towards the core of the Milky Way, again under dark skies, and if we're using a camera to collect more light, you can get a picture like this. So here we see the core of our Milky Way, and the disk of the Milky Way extends in either direction. In the core of the galaxy, star density is much greater. The star Sirius is a bright star in our night sky. Near the core, there would be 1 million stars brighter than Sirius in the so-called night sky, making the night sky 200 times brighter than the full moon. So in other words, you're not really going to have a nighttime sky if you lived on a planet orbiting a star in the core. There are so many stars in a volume of space that it would be very bright even at night. The distance to the nearest star would be a light week. So it would take a week for light to get from your star to the nearest star. Whereas for us, the sun, the nearest star to our sun is about 4 light years. So it takes light 4 years to get from our sun to the nearest star. It would take a light week to travel between stars in the core of our galaxy. Now, a star greater than 25 times the mass of the sun will form a black hole after exhausting its nuclear fuel. And scientists think there are about 100 million black holes in our Milky Way galaxy. At the core, at the center of the core of the galaxy, there's something interesting. A supermassive black hole in the center of the galaxy. It's estimated to have the mass of about 4 million suns. It takes about 220 to 250 million years for our sun to orbit the core of the galaxy. So last time our sun was in this relative location, the dinosaurs were evolving. The diameter of the Milky Way disk is about 100,000 light years. So it would take light 100,000 years to travel across the disk of our galaxy. A light year is the distance light travels in 1 year. It's roughly 6 trillion miles. So the distance across our galaxy would be 600,000 trillion miles. Our sun is about 26,000 light years from the core. So here we see the core of the Milky Way here. We are in the disk of our galaxy, about 26,000 light years from the core. So imagine there was some alien life form, living on a planet near the core of the galaxy. Well, communicating with an intelligent alien that lived near the core would be rather difficult. It would take 26,000 years to send a message at the speed of light to that alien, and it would take 26,000 years to receive a response. The spiral arms of the galaxy are often where nebulae are located, and these are regions of new star formation. Scientists estimate a rate of about 1 star per year in the Milky Way. So these little blue and red splotches here are nebulae, and here we have a magnification of a nebula here. So nebulae would be plural, nebula singular. When a massive star runs out of nuclear fuel, it can explode in what is called a supernova. Heavy elements made in the star and in the explosion are ejected out into space and enrich nearby nebula with these heavy elements. So here we see the supernova blasting out all these different elements, and it will be mixing with the hydrogen and helium gas in this location, and this would be a heavy element enriched nebula. And scientists estimate supernovas occur every 50 to 100 years in the Milky Way. This is a picture of the Crab Nebula. It's the remains of a supernova. And let's return to this image of the galaxy that is similar to our own Milky Way. In fact, up top here we see a star. That star is actually in our Milky Way. But the star here is in the galaxy itself. This star is 400 million light years away. In fact, it's no longer a star. It's the light being emitted by a supernova. So we're looking at a supernova caught here in this galaxy 400 million light years away. And notice it's got a similar brightness as a star in our own galaxy. So supernova explosions are incredibly energetic and bright. One supernova explosion has the brightness of a star in our own galaxy, and yet that supernova is 400 million light years away. Let's define a nebula then. A large cloud of hydrogen and helium enriched with heavier elements from supernova. In addition, small molecules and small particles of rock, metal, and ice, or space dust, is the stuff to make new solar systems. A famous nebula you might be familiar with is the Orion Nebula. And so when we look at a picture like this, we want to think these clouds of gas and space dust, these are the birthplaces of new solar systems, new stars with planets. Another famous example of a nebula is the Horsehead Nebula. Scientists estimate that the Horsehead structure right there has enough material to make about 30 new solar systems. Now it's time to locate our galaxy in the larger scale structure of the universe. Our Milky Way galaxy is just one galaxy in the observable universe, and there are hundreds of billions of other galaxies. Now, the Andromeda Galaxy is a very close neighbor. So the Andromeda Galaxy is about 2.5 million light years away. But there are hundreds of billions of galaxies in our universe. And we're going to use an analogy here. Imagine the entire observable universe were shrunk down to the size of a large classroom. Well, on that scale, a galaxy would be the tiniest speck of dust floating in the air in that classroom. The Milky Way and the Andromeda would be two specks of dust really close to each other. But there are billions, hundreds of billions of other specks of dust in the room, and some at great distances from our own little speck of dust that we call the Milky Way galaxy. So scientists today estimate perhaps 1 to 2 trillion galaxies in the observable universe. Recently, the James Webb Space Telescope snapped this picture, an estimated 50,000 galaxies in a tiny patch of the night sky. And like Hubble in the 1920s, modern astronomers can estimate the distances and the motion of these galaxies. For example, these red galaxies are very far away. Their light is extremely red shifted. That indicates that they're moving away from us at a high velocity relative to nearby galaxies. And today scientists, ever since Hubble, explain this by saying the universe is expanding. Space between the galaxies is expanding, carrying the galaxies away from each other. So in our picture then, we'll just add some arrows here indicating that our observable universe is expanding still today, and it will continue to do so in the future. And so that's our place in space. We live on one little rocky world orbiting one star in a collection of hundreds of billions of stars that we call the Milky Way galaxy, and our galaxy is just one of a trillion galaxies in the observable universe. And so we'll end with a definition of our universe: all that was, all that is, and all that will ever be.